Hi, everybody, and welcome to today is February 23rd. Okay, this discussion is going to focus mainly on the exam, which is held this Thursday. I'm hoping that you guys will bring some questions in here. I know that Robert mentioned something, and he's not here, about something that we did wrong in one of the problems. I hope he has clarified, because I went through all of the problems and honestly, I didn't see any problems with them. Let me move the screen in here.
I think that might have been he was confused between log and ln because some of the equations used ln instead of log and like log instead of ln, and he thought they like meant different things.
I thought he has another issue, honestly. He was saying something about the monoatomic and diatomic gases. That's what I was looking for. I didn't look for log and ln. I was looking for a diatomic and monoatomic gases, and if I use the wrong CV or the wrong CP somewhere. And
That's
honestly,
for lab 4, right?
No, not for lab. He said the problems we solve. Actually, remember when I do the recordings, I go through problems and I solve them and ask you guys to basically finish the calculations or do stuff for them. That's basically the stuff from the lecture.
Yeah.
And so I went through those problems actually, and I tried to see if there is something the matter with one of them, at least related to CP or CV. I didn't see it. The only thing that came close was a problem from, what's it, chapter 18, I believe, that asked you for the translation of kinetic energy, and the translation of kinetic energy has nothing to do with CP or CV. It's pure simple 3/2 of an R times basically KBT for every single atom. Because a molecule can move in the X direction, the Y direction, and the Z direction. So those are the three degrees of freedom. And if I'm only looking at the translation, I'm not looking at the rotation, then I only have 3 degrees of freedom to worry about. That's the only thing that came close, maybe, that confused things, but I was not sure. Since he's not here, I was going to actually ask him, but I was hoping that he would show up to basically tell me where he went wrong.
I'll text him and see if he can come.
Professor?
Yeah. Yes.
In table 2, for the isothermal process, I was doing the homework the other day for MATLAB, and for question 2C, it asked us to calculate the net heat. And one of the processes was isothermal, and it was compressing. So I went back to refer to table 2, and I noticed that for the net heat, it was nRT log V max V min. So I did the calculations, and I got the question wrong. So then I went back to go check in my discussion notes, and actually the net, to calculate the net heat that you gave us in the lecture video, was nRT ln VT over V2 over V1. So instead of it being log, it was ln in like the discussion notes that you gave us.
Yeah.
But then on the table it was log. So
ln, why is it log? Did I say log?
Yeah, in table 2
it said it in the lab. Yeah.
Actually, I'm sorry about that confusion of the ln and the log. It's the integral of 1 over x is an ln, is the natural log, not the because that's all from that integration. Okay.
I noticed that my data for the lab was really off, and I think it's because of that.
Okay. The focus right now is on the exam. Okay, the exam is going to be on Canvas. It's not going to be on Mastering Physics. So here is the deal. There are 4 questions, by the way. Okay, so that you guys know. You will have 2.5 hours to finish the exam. Once you start it, you have to finish it. You cannot go and take a break and come back. You cannot afford your internet to go down during that time. So whatever you have to submit it during that time. You cannot submit it later on, okay? There are a bunch of questions, so I would say, because it's randomized, so I really cannot tell, but there are plenty of questions so that nobody will end up with the same questions as the person next to him, basically, or neighbor, or somebody calls. So you really have to prepare for it honestly, okay? The focus, honestly, is going to be on chapters 19 and 20, so you really have to have those 2 understood. But don't forget chapter 18, the how we interpret basically the kinetic, the temperature as related to the kinetic energy, okay? Kinetic energy being that of translation and rotation, you have to make a clear distinction between the two, okay? the total energy in this case is really that of both of them. But if, okay, Robert is here. Hi, Robert. We're talking about you, okay?
Hey guys.
I was,
Oh, really?
I was
What's up?
defending you, and they were saying things that are. What did you say? What was it? Did you find what you said? Because I couldn't.
Me? I say I hope you all have a good day. Today is my birthday.
Okay, happy birthday.
Happy birthday.
You're born in February, just like me. So I think people who are born in February are the smartest people. Sorry, I didn't mean
I
anything. Okay, listen. There was an issue that you raised. I looked everywhere, okay, for it. I couldn't find it. I went through all the problems that we did. The closest thing I believe to what you were raising the issue was CV not being correct, because you said, correct me if I'm wrong, that when you went through the calculation, I used the wrong value for CV for a diatomic gas instead of I used it for a monoatomic gas instead of a diatomic gas. Is that the question you asked, or am I completely wrong on this?
No, I remember it. Yeah. It was like in the discussion. And it was a while ago. I forget. It wasn't a big deal. Like that was the only thing I could find that was wrong.
Was the only thing I came close from it when I was solving one of the problems from chapter 18, I believe. Chapter 18 had this problem dealing with the translational kinetic energy of the gas. I don't know if you guys remember. You have a gas that was. Let me try to remember roughly what it says. Okay, the problem was. You were supposed to find the, they gave you the temperature, so you're supposed to find the translational kinetic energy, in which case you have to use 3/2 basically, times kBT, where T is the temperature. So you cannot use 5/2, albeit it could be polyatomic gas. It doesn't matter which gas it is, because it's translation, as I was talking earlier before you came in, translation can happen in the x-axis, the y-axis, and the z-axis, so there are 3 degrees of freedom. Forget about the other components for vibrations or rotation or anything like that. So if that's the case, that's the formula we use. We found basically the kinetic energy. And then we took that gas, I believe it was not hydrogen. Yeah, it was hydrogen, which is clearly diatomic. So that's what I thought maybe you were raising the issue with. Because I used 3/2, and you were saying, oh, hydrogen gas, H2, is supposed to be diatomic, so why did I use 3/2? So that's the confusion that I thought maybe was an issue. So now we take it and put it on a plane and shake the plane and have it go super fast. I remember now the problem more. And then you're supposed to compare the two kinetic energies, that of the gas in the plane versus that when it's in motion. And of course, in that case, it's really a small correction, if you wish, to the one when it's on a super fast jet, albeit subsonic, because it was moving with almost 300 meters per second versus the speed of sound, which is 343 meters per second. The point being in here is, you don't confuse the CV and the CP. Every time we have a problem and we're trying to find something that has to do with the energy or something, delta U, then it is CV times delta T, okay? Times the number of moles, don't forget the number of moles, okay? And then CV will matter now. Are we dealing with this diatomic gas, monoatomic gas, or polyatomic gas? Or can you give me what CV is? I cannot answer this question if I don't know what CP is. If I know what CV, I can find what CP is. If I know what CP is, I can find what CV is. If I know what gamma is, then I can find basically what one of the other two are. Both of them, actually, I can find them. Okay? So we need to know one of them at least to find the rest. Okay? And the other issue before you joined in, and we're going to record this one, and hopefully you'll have it ready by this afternoon, is that the issue that apparently there is a confusion between the ln and the log. It's actually the ln every time, because it's the integral of 1 over x basically everywhere.
Yeah, I was about to say on the lab, it all says log.
I extended the lab because I really don't want you guys to focus on it. And some people also had issues logging into Mastering of Physics on Saturday, probably of maintenance or something. They extended that too, just to leave room for you guys to focus on the exam, because the exam is going to happen on Thursday. This Thursday is going to be available at 11 o'clock in the morning and will expire at 11:30 in the evening, 11 o'clock in the evening, I'm sorry. You, as I was saying before, you only have 2.5 hours. Actually, a built-in time so that you figure out a way to scan things and make copies and whatever to upload them to Canvas, because you are required to show your work. Actually, some problems you have to solve them on paper. You cannot do them on Canvas. Some problems you can answer them on Canvas, but you still have to show your work. There is room for each and every one of them to upload your work in there. I noticed in the past that some people they upload everything in one file instead of uploading problem 1 in here, because there are 4 problems, problem 2 in here, problem 3 in here, and then problem 4 in here. What they do is they work out all of the problems and then they upload them at once, okay? And that's fine, but please tell me somewhere in problem 1 and problem 2 and problem 3, for example, if you uploaded everything in problem 4, that, hey, please look at that file, okay? I uploaded all of my work in a single file. That way I know, instead of giving you 0 for problem 1 and 0 for problem 2 and 0 for problem 3, and then realize that you answered everything in problem 4, please be clear in your thing in there. Okay, don't leave it empty. Just tell me what happened in there so that I know, or at least tell me in the beginning, in the first problem, hey, I answered all of the problems in such and such place, so find it in there. That way I don't have to start grading that way. Okay. That is one thing. The other thing also, and I noticed that happened at least with one student somewhere else, not with you guys, is what they do is they go to problem 1 and upload everything, all of the problems in problem 1. So, and then I see another file appended to problem 2. So I go there for problem 2 and I find everything the same thing that was in problem 1, the same thing in problem 2, the same. That is, first of all, too much work and needed, not necessarily. And then it confuses me because I would be tempted now. I'm already gave him credit for problem 1, and I see problem 2, and I gave a credit there. Maybe if I look at this version, I will find a better version to help improve the grade on problem 2, but I find it identical. And I do the same thing nonetheless for the other problems and the other problems. And then at the end, I'm frustrated because I wasted so much time just looking at stuff that is identical. You guys understand? So don't do that too. I mean, there was one student who was doing it somewhere else, and that was really frustrating. So be clear, okay? If you're gonna answer all of them in one place and it's the same thing, upload it only once and tell me where it is, okay? Tell me it's appended to such and such place. Or if you choose to, you can append it separately for every problem as it is asking you to do, okay?
So I don't know
Go ahead.
I don't know the layout of the test. So is it going to be like, can I put all my answers and all my work on one document, like labeled, and just leave the rest blank?
Yeah, you have to label them. Don't let me hunt for them, because sometimes I have difficulty finding them. And then after I grade, I tend to find at least few people who send me messages and say, oh, I had it in there, didn't you see it? And then I look, sure enough, it was there, but I couldn't find it the first time around because it was hidden somewhere in there, okay? For example, they're asked to find a value, and then that value is actually written, but written in the wrong place, so I couldn't find it initially. So it helps a lot to be organized, to get things expedited and clearly graded and things like that, okay? And as I was saying before, these problems are randomized, so you might end up with 2 people having similar problems for one specific problem, but chances are they're different for the other problems, and most likely everybody will end up with the exam completely different than everybody else, so there is no point, basically. It's not just a matter of changing numbers, as a matter of fact, the problems are different, okay? So you may have a completely, especially you just saw from the lab, that you can have so many cycles that are ridiculous. Basically, trying to find your way through them is really, so trying to pick up brain of somebody else that you're struggling with something, they'll tell you, go away, I'm already struggling with mine, leave me alone, okay? And it's different, so don't, it's really counterproductive, and it's not gonna help, and of course, if it's documented, it's really gonna be detrimental to your grade, so don't do that, okay? So that's for the exam. That's really the focus today, is actually on the exam. Do you guys have any questions related to the review problems or anything?
How do you know how do you identify which ones are Q hot and Q cold? Like, I've been doing it like whichever ones are like a positive value and a negative value. But I don't really know how to do it like without that.
Okay. If you go in a process, usually from higher temperature to a lower temperature, you're dumping heat in that case. That's a Q cold, okay? In any process. If you're going from a cold temperature to a higher temperature, you're heating the system, you're adding heat to it somehow, okay? For a case, for example, let me switch cameras quickly in here, you guys, to see if I can draw things. Where's my camera?
So like just to expand that point, what about like isothermal processes?
Isothermal processes are easy, actually. Okay, let me remove the background too. Okay. Isothermal processes are kind of easy a little bit. So this is the PV diagram. I'm sorry if it's backward up to on screen because my camera is situated a little bit. Okay, so this is the process in here. So I'm going through an expansion in here. If I'm doing an expansion on an isothermal, since that's what you mentioned, an isothermal, the gas is expanding if I'm going in this direction. The gas is clearly expanding, okay? So it's going from this initial volume, V1, to this volume, V2. So it's doing work against the environment. If it's doing work against the environment and there is no change in energy, delta U is 0. Okay? If it's doing work against the environment, that means W is negative. As a matter of fact, I can calculate it in this case. It's going to be negative nRT ln of, what is it, V final over V initial, and V final over V initial is positive. So because V2 is greater, so this is more than 1, so the negative in here, we can do the calculation, okay? Remember, you're integrating minus PdV, and P is just equal to nRT over V. So you're integrating, so this is an ln, okay? Integrating dV over V, which is ln of V. So in this case, W is negative. I need to add something to this number to make it 0. I need to add Q in this case to make it 0. This Q must be positive, this number, nRT ln of V2 over V1. So it's clearly V1, Q is positive in this case. That means I am adding heat to the system, and the system is doing work and expanding in such a way there is no change in its total energy. That's what it means to be in an isothermal process. Isothermal process, in this case, it's an expansion. If I do the process backward, that means I'm compressing the gas. Somebody is compressing the gas while not changing its energy. So you're adding through compression. You're going from V2 to V1. You're reducing its volume. You're basically moving the piston in the opposite direction. And in doing so, you're not changing its internal energy is the same because it's an isothermal process, okay? So the system has to dump that external energy in some form of heat. So if W is positive, if that means V final is less than V initial, that means this ratio is less than 1, which means the ln is negative times negative is positive. That means W is positive. Q better be negative to be able to do that. So I'm not adding heat if I go in the opposite direction. I'm actually removing heat from the gas, from the system. So the heat is actually being dumped to the environment because I am adding energy through this change in volume by moving the piston, okay? Of course, I'm compressing it. Now the pressure was here, now the pressure is there. It's higher pressure, okay? I'm compressing it. This is how much pressure if I go in the opposite direction. So I'm looking at the scenario backwards so that you guys hopefully are following me. If I do it the opposite, meaning that I'm compressing it here, so I'm going from this pressure to this pressure. That means I'm compressing it, putting higher and higher pressure because I'm moving the piston so that the volume is less and less. And there is no change in temperature because that's what isothermal means. That means delta U is 0. Remember, delta U is NC times delta T, and delta T is 0, so delta U is 0 for an isothermal process. Therefore, in this case, the energy that I am adding through working against the gas must go somewhere, and is going to go and be dumped in the environment. So that is actually out, Q out. Does this make sense?
So just to review, so if the gas is compressing, the work is positive. If it's expanding, the work is negative.
Yeah, because if not compressing in a sense the pressure, if the gas, the volume of the gas is less and less, that means it's you're doing work against it. Somebody has to actually compress the gas, has to actually make the gas, the volume less and less. Okay, something has to make it less and less. Okay.
Yeah.
And in a cycle, you're doing both actually. Let me show you a cycle, because it's very important for the exam, this discussion on the cycle. You really have to make sure that you guys understand what the cycle means. Cycle, you start from a point and you come back to it, which means at the end, no change in energy whatsoever, no change in entropy whatsoever, okay? Because those are state variables. So if they ask you what is the change in the cycle, it's going to be 0 for both quantities, regardless of what process you went through, even if you didn't go through an isothermal process, okay? So here is another PV diagram in here. I'm going to go through a cycle. We have two options. Either we go counterclockwise, okay? Counterclockwise. I drew it counterclockwise. It may look clockwise in your screen, okay? So this is counterclockwise. Clockwise. When you do an angle in counterclockwise, is the angle positive or negative when it's counterclockwise?
What do you mean angle?
I'm sorry. This is clockwise. I drew it clockwise. I didn't draw it clockwise. What am I? When you measure the angles, remember from your physics 1 and physics 2 measurements of the angle, I drew it clockwise. I'm sorry.
Wait, so when you do it
Clockwise.
negative.
So the angle is negative. Do you guys remember that? When you do the angles, yes?
It's the trig circle.
Yeah, trig idea stuff, okay? So the work is negative too. That's why I use in my definition, I didn't follow the book, I followed every other text for the work. It's the integral of this quantity, okay, minus PdV, okay? So the work will turn out to be negative. So where is that work coming from? That means the system is doing work. This is an engine. That is the thing that does work, okay? If I'm going through the process in the opposite direction, if I'm now indeed going counterclockwise, this is counterclockwise, by the way, okay? Counterclockwise in the angles, do you guys remember from your physics 4 or physics 1 or physics 2 or whatever classes that you had? Is the angle positive or negative when you go counterclockwise?
Positive.
Positive, beautiful. The work also will turn out to be positive, okay? If you do this integral also, it's going to be positive. That means that you have to supply energy to the system to work, okay? And in doing so, you're extracting heat actually from the cold source and dumping it in the hot source and adding energy to do that. That's how the refrigerator works. This is what a heat pump is. A heat pump is exactly like this. It takes heat, pumps heat from the cold source and dump it in the hot source, which is the opposite of what the engine is, okay? So you would want as much heat extracted from the cold source versus how much it costs you to do it, which is the work. That's why you pay the bill for the refrigerator, because the bill is coming from the electrical energy being converted to work to extract heat from the food that is already cold into making it colder and dumping the heat behind the refrigerator. If you go behind the refrigerator, you see that. So the heat pump or refrigerator is the opposite of what the engine is.
I have a question about that for refrigerators. So for engines, the efficiency is the network over QH. So for refrigerators, would network over QC.
It's the opposite. QC over the network. Okay? That is actually the coefficient of performance.
But it is QC, and then.
Yeah, because your ultimate goal is to make it cooler. You don't care about Q hat in that sense.
So it's.
But both of them.
It's more like QH than like QC and QH. like the heat going into it.
Yes. Yeah. The point in here being, by the way, the coefficient of performance is more than 1 usually. Okay. How good you're extracting from this one usually is more than 1, whereas the efficiency of an engine is less than 1. I forgot what I was going to say. Yeah, always look at the scenario that you have in hand, okay? So you have to be careful with these things. That's, again, chapter 19 and 20, which really should be only one chapter. Don't forget about the entropy also and how to calculate it and things like that. Forgot what I was going to say.
Yeah, 19 and 20 seem really similar.
Yeah, actually 20 was the second law. Yeah, I'm sorry. This is the point I was going to say. Regardless of the scenario, whether it's an engine or a heat pump, both of them, they actually still satisfy the fact that the work in this situation is going to be the difference between the Q hot and the QC. Okay. Absolute values, okay, just like this, okay? Everything is in absolute value. In other words, this is how the refrigerator works, actually. You take work in, and you extract the heat from this one, and you dump it outside. And this is in absolute values, of course. We don't care about the signs at this point. And to get the Q hot in it, okay? That's how the first law, basically. This is the first law, nothing else, okay? In this, so this is TC, this is the lower temperature, and this is the hotter temperature. You want your food to be cold, so that's how you would want to extract heat from it, okay? So it may be to keep it cooler, or make it even frozen, more frozen. In the case of the engine, this is still T hot, and this is still TC. In the case of the engine, it extracts heat from the hot source and may give you work from it, and dump some of the extra heat into the cold source. So this is your Q hot, this is your Q. I'm taking it in absolute values. Okay, it's still the sum of these two is still equal to QH. Okay, this is basically one of the questions that you guys had when we did the pre-test. It has to do with just this relationship. How is basically W and QH and QC are related in such a way that you find the efficiency in this case for an engine. It's going to be how much work you get out of it. This is the net thing that you obtain from it, versus how much it costs you to do that, which is you have to heat up something, okay? Like the Stirling engine that I showed you guys in the video that I conducted in here, which I still have it in here, which is one of the best engines there is, actually. Yeah, except it's not, this is the closest you can get from a Carnot cycle, okay? This is the Stirling engine. You heat this thing in here, so that's your hot source. It goes through, what is it? An isothermal process in here during the heat exchange, and there is an isochoric process during one cycle, and then there is an isothermal compression during this cycle, and then another isochoric process, and the whole process repeats again. Okay.
Oh, does the Carnot engine not exist?
No, you can't build it. It's very, very ideal that you. It's very. I mean, if you can build it, you're going to be probably the next Nobel Prize winner. Okay, so it's very hard.
Isn't it just purely hypothetical?
Yes, a hypothetical. It's very hard to do. That's why it's the most efficient. I mean, that's why nobody can beat Mr. Carnot at it.
I thought it existed. It was just like made of pure gold or something. So no one made it.
It's a hypothetical. Actually, even the Stirling engine, it's very hard to make it into a real engine to work in industry. I mean, you can make one, like this toy ones, the ones that I got from Amazon, actually. Or you can buy it yourselves, but it's not in the industry. It's very hard to build a big real model out of it and put it in a car or something. In cars, we use the... Sorry?
Yeah. Well, why is it so hard to make it that efficient? Or like
it's usually the isothermal process, I think. That's the problem with it. And also the change in the... I know, look, I'm not an engineer. You guys talking to a physicist about engineering questions, sorry.
Oh, okay.
I know it's very hard, okay? I can tell you why the Carnot engine is hard to do, okay? But that's a question apparently for engineers. If you can successfully build the Stirling engine, you're gonna make a lot of money, because remember, cars are running off of auto engine, which is even worse than this one's. The entropy, when you write dq over t, that's a question from Adrian. You have to find how dq. Okay, that depends on the case. Okay, that's a good question. Depends on the case. This is Adrian's question. Okay. Basically, in the case where I know how dq depends on dt, for example, in an isothermal process, dq is actually, let me put it this way, there is no dt in that situation at all. In the isothermal process, T is constant. So I can't really do, so yes, ds, the entropy in this case is dq over dt, et, but T is constant. So the integral will simply be, for delta S, will simply be equal to 1 over T, because it's constant. The integral of dq, which is just simply q over T. Does this make sense to you, Adrian, and everybody else? That is an isothermal process. That's not the only process, though. Okay, how about another process, for example, in the case of the isochoric process, or the process for the pressure, what is it? The isobaric process. So isochoric, isobaric, or even the case where you take calorimetry. Remember, in calorimetry, the heat was, I'm going to use the dq in here, was equal to mc, mass of the component, times the specific heat, times the change in temperature. That too, all of this one, in this case, it's dq is equal to ncv dt, and in this case, it's equal to ncp dt. All of them, they're proportional to dt, basically, for dq. In any of these cases, there is a number times dt. There is a number times dt, and there is a number times dt. So dq over t will be some number in here, which I'm not going to write, times dt over t. So any of these three cases, this is calorimetry. Basically, for example, one of the examples is that we did actually was you take your cup of coffee and you warm it up, okay? Or water and you warm it up from room temperature to some temperature. So you're going to use this expression in that case, okay? And then it's going to be dt over t, so you can find how much increase in the entropy is, okay? So you can do that calculation. Now it's going to involve the ln if I integrate to find delta S. It's going to be some number, depending on which one I'm dealing with, times ln of t, which is between t initial and t final, which is ln of t final over ln of t initial. Does this make sense to you, Adrian? At least for this 4 cases. The case of the isothermal is the easiest. These 3 cases are kind of easy to some extent. In general, it's very hard. You have to give me how dq or depends on t, okay? Another case that is trivial is actually the adiabatic process. That is actually delta S is equal to 0 then, because dq is 0, okay? That's why the adiabatic process is sometimes called the isentropic process, because of the fact that the entropy is constant, doesn't change. So delta S is 0 in that case. Okay? That's a good question. Any other question related to this exam? Please look at the examples that I did. Make sure that you have them understood. And also the problems from the homework. And go beyond those a little. Make sure that you have an understanding of the chapters. You know exactly what they're talking about. And as I said, the exam is no secret from day one. I told you guys it's going to be the focus is going to be on chapters 19 and 20 in this exam 1. Okay. Chapter 18 also, don't forget about it. It's very, very important, because without chapter 18, we had no clue what temperature was. We thought temperature was some sort of a fluid or something. But chapter 18, the work of Mr. Boltzmann clarified it. It has to do with the kinetic energy of this fast-moving particles, basically. And that's important, so we cannot really not test on it. You will, Winter, that's a good question also, okay? If you know how to solve these questions, you're going to get probably a lot of credit for them, but at some point, some of these problems, you're going to have to show your work and upload them uptright, okay? And you will get a lot of credit, especially for you, since I had you before in the past, so you know that you will get a lot of credit if you do show your work. And at the end, let's say, for example, you messed up the conversion or something like that, and you ended up with the wrong value, and that wrong value ended up messing up the answer for the next question and the question after that. As long as you have the reasoning is correct, you can still end up with a lot of credit for this one. That's why showing your work has a lot of benefit for you more than anything else.
So you do partial credit then, right?
Yes.
Okay.
Let's say, for example, question 1 asks you to find, I don't know, just to give an example in here, the temperature, okay? And then after that, you're supposed to find the pressure. And after that, you're supposed to find the volume. Let's say, for example, you messed up, for example, which is a big mistake, by the way. You're going to lose big points on it if you don't, if you're not careful enough and you forget to convert from Celsius to Kelvin. Okay, albeit these numbers are going to be given in centigrade Celsius. You have to add 273 on it. Okay, let's say, for example, you forgot to do that, and now you have a problem with the temperature because it's completely wrong. Then you calculated the pressure, but the calculation is right had you plugged in the correct conversion. There is no double jeopardy in this case. You're not going to lose points again just because you forgot to do the first one correctly. Does this make more sense to you, Michael?
Yeah, that sounds good.
Okay. How much should I review Chapter 17? Chapter 17 has implications also on Chapter 20. I just mentioned the fact that the entropy, for example, could potentially has to do with calorimetry, and that's exactly what Chapter 17 was, okay? So you need to understand a little bit. I know you did a lot of that thing in chemistry and probably you're sick and tired of it, but it's important. It relates to all of this.
I kind of thought this class was just going to be like chem at first, because like first 2 chapters are so chemistry based from what I learned there, but it got like more into like mechanics.
Yeah.
Later chapters.
Yeah. I think the picture should have been completely backward because this really stuff that should happen before the chemistry. Chemistry is just an application of these things and their chemical reactions. And actually it should happen immediately after Chapter 20, after we do Chapter 20 and we know what the entropy is. Then you go into a chemical reaction and see, is it feasible? If I calculate the entropy and the enthalpy, would I be able to get a chemical reaction? Would this reaction is possible, or would I need something they call catalysts or even energy to the system to make it happen? Okay, makes chemistry more understandable that way. But unfortunately, you took it after the chemistry, which is okay. Okay, the club rush on Friday. I'm kind of a little bit not too much involved with that as much as I was hoping to be, but because I'm engaged with something else. Actually, we're trying to do a competition in another college where I am actually, because I'm relying on Dr. Adams to really work on this one as much as possible because I have to do something somewhere else with another team. You have a question, Robert, on that?
I'm the math club president. So I'm just trying to get people to go to the club rush. Can I put the link in the chat? And like,
that's fine. That's fine.
Okay, so it's the club rush is on Friday, and it's like an hour or 2 long. And I think like all the timing and stuff is in the link. And there's gonna be like over $1,300 in prizes. I think it's like $1,500. So you can win like an iPad just by participating in a Kahoot game. There's going to be a lot of prizes up too. So, I mean, plus like if you just
you guys, or can I participate too?
I think you can. participate. And then if you're just bored out of your mind, there's going to be a lot of like cool clubs there trying to entertain you, you know, like maybe meet some new people. So I hope to see you there and join the math club and the physics club.
Okay. Any questions related to the exam? You have to be systematic. You may be actually doing it backward for this specific exam. I would recommend that you go through chapter 20 because it makes more sense, at least in terms of the problems. It makes problem 19 more chapter 19 more understood that way. And because some of the problems from chapter 19 can easily be converted to adding entropies to them and adding efficiencies to them and things like that from chapter 20. So that's the advice I can give you about that. The key thing from chapter 18 is the idea that has to do with how kinetic energy is related to temperature. That is very important. That explains to us that idea. And you need to know how to calculate the kinetic energy in a gas, if you know its pressure, its volume, its temperature, and all of its properties, basically the number of moles and things like that. And you need to understand that that kinetic energy is actually the average. I mean, that temperature is actually the average kinetic energy of a single molecule, okay, in the gas. And I know we have an Avogadro number of them, but that's, or at least a number of the order of Avogadro's number of them when they are moving with all of them in the gas. And I know you did sound way back with the physics 250, I guess. You did sound there or not? You did it. You did. And sound is actually related to chapter 18, actually, related to this idea of how the thermal, how the temperature is related to the kinetic energy of the moving particles, because the speed of sound is related to that. It's very, very beautiful theory. If you're not too clear on this issue, you can actually go to chapter 47 from Feynman Lectures. It's on volume 1, okay? And also chapter 17, the key thing in there is the idea of temperature and how to measure it. But I'm not usually, honestly, I don't test people on how to do conversions from centigrade to Kelvin to Fahrenheit, because I thought it's not really appropriate for a calc-based course. As a matter of fact, you will need it though, because I was just making a big fuss over the fact that you may forget to make that conversion, especially between centigrade and Kelvin, and that could throw you off. Okay, your answer is off, and you lose unnecessarily points for nothing. Okay, but calorimetry is important because that helps us, at least in terms of understanding entropy and things like this. Okay, any questions?
Will there be questions where we have to gather data like on a table and then do like a simulation, or will it just be mostly just like, you know, work out the problem and then just solve it?
This may be okay. I cannot tell you no or yes, okay, because usually through my exams I really give data and work with data, okay. So I expect you to know how to handle data and interpret data and do data stuff, okay. And I test on it regularly. So the examples I do in the problem solving and the homework that I do with you guys has that component on it. So basically expect things with data, expect things with calculus, basically where you're expected to know how to do integrals and things like that. And expect things also with algebra, where in this case probably it's not much, but where you're going to be probably involved with geometry. In this case probably there is not. But yes, the answer to your question, absolutely. Okay.
Okay, thank you.
Mm-hmm. Any other question? You guys think of something, please send it related to the exam from now until Friday, until Thursday, 11 p.m., which is technically Friday morning. After that, then we can discuss other things like labs or whatever. The focus from now on is on the exam. Yes? Once you ask a question, once you ask a question, and if I think the question is worth everybody's basically attention, then what I do is I'm going to probably come in here to Canvas and go to the announcement and post my thoughts on it. You have any question, Winter, or anybody else? Yes, I mean, if you want to. Oh, the exam has 2.5 hours. I'm sorry. 2.5 hours. Is that your question, Winter? Okay, it's 2.5 hours. I already factored in the time for the upload, okay? So if you run out of time, it's already on your account. So if the internet goes down, it's your problem. If so, you really have to make sure everything is working before that time, before you click on open. You only have one attempt at it. You don't have 2 attempts, okay? Once you're in front of the screen, you have to really go through all of the solutions, make sure everything is working, and then submit your work, and then on your way. The reason why I do it from 11 o'clock in the morning to 11 at night, because I understand some of you are probably working and may not be excused from your job because you're required for it during daytime or nighttime. So in either case, you're both covered, unless you have a weird shift, which starts at, I don't know, from 11 a.m. till 11 p.m., then you really have to figure out your solution on your own, okay? There is nothing I can do on that. Anything after 11 p.m. is too late for my, cannot stay there and receive a message. Now, if there is an issue, please message me right away. I prefer, honestly, to be messaged immediately via Canvas. And I will be in front of computer at that time. So if there is a message, I should see it and know exactly if there is a problem with Canvas or there is a problem with a specific problem, or I gave you probably the wrong conversion factor or something like that. Then I will go and say, okay, if you have a problem like this one, this is the correct way of doing it, okay? And in any case, make that into part of your solution in there. Any other question?
For the chapter 18 homework, there was a question about buoyancy this man has put into a diving bell. I eventually figured it out, but what I initially thought was that the bell was already neutrally buoyant, and then the man stepped inside of it, and then how much water we displaced after that. I just like when I did the map, it turns out that the man stepped into the bell before it was placed in the water. Then he was submerged. I just wanted to know, like how would you figure that out?
I don't know which problem that it is. If you can send me the problem, and then I will think about it and let you know. Okay. Sometimes we tend to do things. I was actually in another class with another group of students who are math inclined, and when you're math inclined, you're looking for that math, basically logic, and sometimes there is a physics logic that is a little bit different than the math logic. Okay. Send me that. We'll discuss this after the exam, okay, Robert? I really want you to focus on the exam, okay? Because as I was saying, from chapter 18, the focus is on the kinetic theory as it's related to the kinetic theory of gases as it relates to kinetic energy versus that of the temperature. Okay?
Absolutely. I don't have to worry about the buoyancy stuff. Okay.
No, not in this exam. Worry about it in the labs and other things, but not in this exam. Okay?
I spent like 4 hours on that question.
Yeah, buoyancy is a lot of fun if we're not doing calculus physics. Okay? You have to bring your calculus hat into that class in that time. Okay. You guys have any questions? Chad, I didn't hear anything from you. Daniel also. Daniel was talked to a little before.
I'm good for now.
Okay.
Yeah, I was just here to listen to other people's questions, and
okay.
I'm good though. I think I have a good grasp on it.
Okay, very good. Glad to hear that. So here is the deal. We're gonna end this session. And is it recording? Yeah, I'm glad it is, because I thought I forgot to record this thing for the rest of you guys. and post it later on for everybody else's benefit. And hopefully you guys have no issues with this exam. And then we'll continue the debate. Chapter 37 lab is actually on Canvas too. And that is a doozy. So I'm going to really leave that discussion until later on, because that's actually, there are so many paradoxes in that lab that you really need to resolve. So I'm looking forward to that. So let's leave that after the exam. Okay. Okay, unless you guys have any questions or something else, I'm going to stop the recording right now. And I will see you, depending, okay, maybe next week, okay? I will let you know exactly the time and the link. Thank you, guys.
Yeah, I'll see you
Thanks,
later.
Professor.
Bye.
Bye.
Thank you.
Yeah, thank you.